Well, we will be using mostly this form of the uncertainty principle. Well, let's do a problem and see how that looks like. The speeds of an electron and a 20-gram bullet are both measured to be 300 meters per second at an instant. If the uncertainty in this measurement is plus or minus 0.010%, what is the minimum uncertainty in the position of each? What is the minimum uncertainty? Now, since we are looking for the minimum uncertainty, we can replace that inequality sign by an equal sign. That will be the minimum value. Well, what are the given data? The mass of the bullet is given. Mass of the electron, you know. The velocity of the bullet and the electron both are given. Now, the uncertainty in measuring the velocity is given. I want you to interpret correctly. It is 0.01%, means it is 0.01% of 300. So your delta V will be 0.01%. When you convert that to be a number, it will be 0.01 divided by 100, which is 0.0001 of 300. So we say delta V is plus or minus 0.0001 times 300, and that will be plus or minus 0.03 meter per second. That is the uncertainty in measuring the velocity. Now, it means the uncertainty can be anywhere from negative 0.03 to positive 0.03. So, the actual spread is 0.06. And therefore, we must use delta V as 0.06. That is the actual uncertainty. So, the actual uncertainty is double this value, because you can have 0.01% above or below the actual value. Therefore, in our calculation, we got to use delta V equal to 0.06 meter per second. Now, for maximum uncertainty, no. You try to change this to minimum. Is that right? That's what we want to find. To find the minimum uncertainty for the bullet, we need to find the minimum uncertainty for the bullet as well as the electron. So, if you change that maximum to a minimum, what will our equation be? It will be delta x equal to h over 2 pi delta p, because delta x times delta p equal to h over 2 pi. And therefore, the minimum uncertainty in locating the bullet will be h over 2 pi times delta p, and delta p is the change in momentum, uncertainty in the momentum, which is mass times delta v. So we replace that. That will be h over 2 pi times mass of the bullet times delta v. I hope you understood this statement. We are looking for the minimum uncertainty in the position. Now, when the uncertainty is minimum, delta x multiplied by delta p equal to h over 2 pi. Alright, what all we now need to do is replace these values. We know the mass of the bullet, we know delta v, we just calculated, and h we know, and that gives you the uncertainty in measuring the position of the bullet is 8.8 times 10 to the negative 32 meter. You can see this is a very small value. So we can say for all practical purposes there is no uncertainty in measuring the position of the bullet. Because the bullet is a big object, the uncertainty in measuring the position when we have measured the uncertainty in its velocity is not very significant. But what happens in the case of an electron? If you now replace this for an electron, what will be the difference? Well, the only difference is the mass here will be the mass of the electron, And in such a case, look at the uncertainty. It is 0.0019 meter. So there is an uncertainty of 0.0019 meter. Now remember, considering the size of the electron, this is a humongous number. So there is a very large measure of uncertainty in locating the position of the electron when the uncertainty in its momentum is given to us. I hope that particular point is illustrated by this problem. Now let's use this concept in developing an atom model. What is an electron orbital? These concepts are actually used in developing the concept of an electron orbital. So we are going to improve the Bohr model. In the Bohr model, an orbit n equal to 1, n equal to 2 are all clearly defined. But that model cannot be applied to higher elements. So let's see how quantum mechanical model can be applied there. According to quantum mechanical model, the location of an electron is specified by an orbital, contrary to what an orbit did in the Bohr model. An orbital indicates the probable location of the electron. You see, quantum mechanics only gives you the probability that an electron can be found in a certain location. It doesn't tell you exactly where it is. So an orbital indicates a probable location of the electron in an atom instead of a definite path they follow. So that clear orbit in the case of a Bohr model is now looking a little fuzzy. It is not very clear because you don't have a clear path of the electron. We don't know exactly where the electron can be found. So this gives rise to the idea of an electron cloud around the nucleus. That means there are regions where the probability of finding the electron is greater than other regions. But the probability value of finding the electron around the nucleus varies at different places, giving rise to the idea of an electron cloud. Now here, not a very good picture though, but it gives you an idea of what an electron cloud looks like. Now, the cloud density reflects the probability that the electron is in a particular region. If the cloud density is large, it means the probability for finding the electron there is greater. If the cloud density is not very high, the probability of finding the electron there is very low. The probable location of the electron in an orbital is described by a series of numbers called quantum numbers. Now you are familiar with one quantum number we used in Bohr model. What was that quantum number called? We call it the principal quantum number. N equal to 1, the first orbit, n equal to 2, the second orbit or the energy level, and so on. Now we're going to expand that in the quantum mechanical model. In the quantum mechanical model, you don't have an electron sitting exactly at n equal to 1. But we will use that quantum number again here. But we will add more quantum numbers. Well, that makes it a little more complicated. We have a set of 4 quantum numbers in here. The quantum model of the atom uses 4 quantum numbers to describe the arrangements of electron in an atom. So in addition to the principal quantum number, we will use 3 more additional quantum numbers to describe exactly where the electron is. Now, the first is the principal quantum number, n equal to 1, 2, 3, and so on. The second is the orbital quantum number, and we represent it by L, and L can have n minus 1 values. That means for each n, there can be different L values. So if n equal to 3, what are the possible L values? L can be 0, 1, or 2. There are n minus 1 values. For n equal to 3, L can be 2, 1 or 0. There are 3 possible values of L for one n value there, n equal to 3. Now the third is the magnetic quantum number. We write it as m sub L, and that can have values. M sub L is plus or minus L. So how many ml values can there be for n equal to 3? Can you tell me? ml is plus or minus L. That means for n equal to 3, ml can have 2, 1, 0, then minus 1, minus 2, or minus 1, minus 2, minus 1, 0, 1, and 2. There are 5 different values of ml for n equal to 3. And the fourth quantum number is called the magnetic spin quantum number, and they have just 2 values. It can be positive 1/2 or a negative 1/2. So we have now all these quantum numbers, and we're going to use all these quantum numbers to locate exactly where an electron is in the atom. In other words, these quantum numbers actually gives you an address to locate the position of the atom. And now this is where quantum mechanical model is actually more precise than any other model we discussed so far. Now, it is common to refer the energy level corresponding to a given n value as a shell. So n equal to 1 will be the first electron shell, n equal to 2 will be the second shell, and so on. And then there will be subshells corresponding to L values. So there are shells and then subshells, and we will have a look at that. I have made a very primitive diagram here. If you look at n equal to 1, well, n equal to 1 don't have any more subshell, because n equal to 1, L can have only one value, that is 0. Is that right? So for the n equal to 1 shell, there is only one subshell, which is itself. But n equal to 2, L can have 0 and 1. Is that right? 0 and 1, n equal to 2. That means there are 2 subshells there. So the n equal to 2 becomes a little more complex. N equal to 3 becomes a lot more complex. So you have now, in place of Bohr model having clear orbits, here we have shells, and each shell has subshells. Well, subshells are named S, P, D, F, G, and so on. Now, the subshell S stands for the value of L equal to 0. The subshell P stands for the value L equal to 1, and so on. So subshell G stands for L equal to 0, 1, 2, 3, 4. So for each L value, we name the subshell. Now, to specify an electron, we use n as a number and followed by the letter that stands for L. In other words, when you specify an electron, you got to say which shell and which subshell. Okay. Now, for example, 1s corresponds to an electron in the shell 1 in the S subshell. Now, 2p, you see, you can see that is the address of the electron. 2p is an electron that is in the shell n equal to 2 and its subshell corresponding to L equal to 1. Now, how about the 3D? 3D corresponds to the third shell, n equal to 3, and its subshell corresponds to L equal to 2. L equal to 2. Or n equal to, yes, so n equal to 3 and L equal to 2.